Okay, welcome to your optimization worksheet homework solutions. A little bit different this time because it's not going to be static, so I'll be talking you through the solutions. Now, this original assignment 1, 2, 3, 4, 7, and 11, remember 1 and 4 were on that first worksheet, so we're not going to duplicate those solutions. Okay, let's jump right into number 2. Feel free to pause as you need to copy. Find the dimensions of a rectangle. The area, which is length times width, is going to be a fixed 1,000 meters squared. Okay? The perimeter of this rectangle, 2 length and 2 W's, that's going to be as small as possible. Okay? So I have my constraint, I have my secondary information, that's to relate the variables so that I can talk about perimeter in terms of one variable. It doesn't matter which I solve for, and I don't have to do another optimization to find the second one. Well, let's find W. W in terms of L is 1,000 over L. And with that substitution in here, and my perimeter in terms of L, getting rid of W, will be something like this. Not simplified yet, not in the best way maybe to take the derivative. Let's go 2,000 times L to the negative 1. Okay? My derivative is a 2 minus 2,000. The negative 1 comes down. L to the negative 2. I'm going to put it to my denominator now. Alright, I'm going to set this equal to 0 for our critical numbers. In finding the critical number, I'm going to move this 2,000 over so that all my terms are positive here. You already have the undefined derivative at L equals 0 as a critical number. That's not really in our feasible domain. We're not going to be able to make our fixed area there if L were a 0, so we're going to ignore that one. 2,000 over L squared equals a 2. Cross multiplying, or even just this, proportion property where you can switch the diagonals there. 2,000 over 2, or 1,000, where is it, a 1, equals L squared. Sorry, my stylus has gotten kind of squishy on me, so we're just going to have to deal with it. L is going to be the square root of that 1,000, or 10 radical 10. Okay. Now, we've seen this problem before in minimizing that perimeter. We go back to find W, which was 1,000 over L. And 1,000 over that square root of 1,000 ends up being another square root of 1,000 for the 10 radical 10. They ask you for the dimensions. You can tell them the length and width individually. A lot of time we'll just say length times width. Ten radical 10 by 10 radical 10. And so in optimizing area, or excuse me, perimeter, around a fixed area, it does turn into a square. Alright, so welcome to the jumbo can of Beanie Weenies. We have a constraint here that volume has to be 10 cubic inches. Material for top and bottom of the can is 5 cents per square inch. Material for the body of the can is 7 cents per square inch. And let's minimize cost to the nearest cent. And you can do the problem in cents or dollars, but that would be the nearest cent or the nearest hundredth of a dollar. Volume is pi r squared height That base is a circle of the cylinder, stacked up h times, and you get the full volume. Surface area, we're going to need surface area. Surface area for a prism and cylinder are similar. Basically, we double the parallel bases, whatever that shape is. In this case, it's going to be a circle. That's for the top and bottom. And we are going to have to add our lateral area. Lateral area, is everything that's on the side, right? The tube. And so if we unfold that, basically what we have is just a rectangle. Okay? But the rectangle is either circumference or in this case perimeter to find the length, and then the height is the other piece. So it's just the length times width area, but you have to understand what you're dealing with. It's very helpful for a prism. You just add up its perimeter times height. Okay? Lateral area is perimeter times height, generally. Okay. Our substitution is going to use this volume as a fixed 10 pi. I think I misspoke earlier. Don't forget that pi. 10 pi is what pi r squared h equals. The pi's cancel out. And we're going to only need this h. Okay? There's one less power to deal with. Real easy just to divide by the r squared. And you'll see in the other optimization equation that there was a singular h when every term already had r's. Okay, what is that optimization equation now? We want to minimize costs. Remember, dollars have to be included here. My cost in terms of r, I'm ready to get rid of h, is going to be 5 cents, okay, which is 0.05 if you want to do this in dollars. I'm going to do it in whole cents so I don't have to deal with the decimals. Okay, so when I get an answer like 400, I'm going to move the decimal later to call that $4. Got it? 5 cents is top and bottom. There's two of those. And the formula for their area is pi r squared to get those square inches. Multiplying my 5 by my square inches area. Okay. Adding the 7. Now the lateral area is 2 pi r times h. 2 pi r h. The stylus is freaking out a little bit, but these parentheses are going to show up. Okay. So it's not in terms of r completely yet. Let's simplify this. 10 pi r squared, 14 pi r times. I have 10 over r squared. Notice the r's cancel. Okay. This exponent is going to become a 1. And for the sake of my derivative, we're going to, let's see, 14 tens is 140. Don't forget this pi. And r comes to the front, to the numerator, sorry, with a -1 exponent. Okay, if you heard the dog growl, he needs to go out, so give me a sec. Alright, all that work for the setup. Now we're ready to finally apply the derivative. C prime ends up being 20 pi r minus the 140 pi over r squared. That's just that r becoming from the -1 to the 2, and r to the -2 moving to the denominator. Setting it equal to 0. Again, moving that negative to the left. 140 pi over r squared equals 20 pi r. Now I'm going to multiply through by the r squared and divide by the 20. So I'm going to have only r's on the right hand side. You're going to see it 140 pi over 20 pi. Again, pi's cancel. This is r cubed though. And 20 goes into 140 7 times. Oh, lost my pen. So r equals the cubed root of 7. Okay. We want to plug this back in here to the original cost in terms of R to find out what that cheapest can is going to cost. I'm not going to get into the first derivative test for that value right now, but I will tell you, as far as positive values, we are looking at a dip over on this side, and interesting asymptotic thing happening there for that rational function. Okay, so outside of the feasible domain, we don't really care about anything happening over here, and this is that cubed root of 7, or like a 1.9 something maybe, as a decimal. I'm going to leave that cubed root of 7 when I plug it in. That pi, I'm going to use the pi button on the calculator to be exact also. So no need to change this yet. No need to change these. I will round to the nearest cent for the final answer. Let's see what we get. Alright, so I'm getting a number from the calculator of a final cost C of the cubed root of 7 as approximately 344.88. Now that's in cents. Remember, I didn't use decimals earlier. That's $3.45, or if you want to leave it in cents, $3.45. Okay. That's kind of an expensive can, but that's how the numbers work. We're going to put 7 and 11 in another video. We're coming up in the 12th minute of this one. I try and keep them a little bit short. Alright? I hope this helped.